All right, in our last video, we took a deep look at comets and we analyzed how different energy levels could affect the behavior and shape of its orbit around a central object, such as the sun. In this video, what we're going to do is we're going to continue our discussion on solving the Kepler problem. In essence, the two-body central force problem in which we have a planet, such as the sun, revolving or rather, let's back a little bit, a planet such as the Earth revolving around a star such as the sun, basically a very massive object. So what I want to ask you first in this video is, how did we describe the orbits in our example with the comets? With the comets, we found that it's easy to explain an orbit in terms of the radius along different angles in that orbit, because we know the orbit has to go around at 360 degrees, and along each trajectory for each given angle, we have a different distance, r, that defines the shape of our orbit. And we're trying to figure out mathematically, we're trying to prove Kepler's laws, which indicate that the orbit is going to have some kind of shape, which you probably already know the answer to, but I'm going to save that for when we actually prove it mathematically using our physics principles, okay? So we found that in the comet example, it's best to explain orbits and the shape in terms of r, and to express r as a function of some angle phi. Now, my question for you is, well, I have a few questions. Here's the equation of motion that we worked so diligently on finding in the last few videos in this course. In essence, we were able to reduce a two-body central force problem with 6 degrees of freedom down to a one-body central force problem with 1 degree of freedom. We were able to do this by ingeniously changing our perspectives, changing at how we look at the problem in front of us, how we gather data, how we analyze what we have right in front of us. But by looking at it differently. And that gave us some insane analytical abilities, drastically elevated our capability and how effective we can be in solving this. Now, my question for you is, when you look at this is a very odd differential equation. It's second order, we got r double dot, and on this side, we have 1 over r squared. So the question becomes, how in the world do we solve this? And I personally don't know how to solve it. You probably don't know how to solve it. So what does that mean? It means we have to employ our knowledge, employ our tricks, and employ our understanding of physics to try to reshape this in a way that makes it solvable. Okay, what can we do? What can we do? Now, the general theme of this course is that perspective prize our once weighty eyes, and it gives us wings, okay? By looking at things differently, by taking a different perspective, that can drastically enhance our analytical approach, okay? And we saw this previously with deriving this differential equation in the sense that we could look at the problem differently, change our frame of reference, and that could allow us to get down to this nice, amazing simplification. But to make progress, to make headway, the way in which we use this principle is by changing our mathematical perspective, the way in which the mathematics is expressed here. And the way in which we're going to do that is we're going to take this r function, which defines the radius of our orbit with respect to our origin, or rather the r is basically the separation point between the two, basically this guy right here. We're going to take this, and instead of being a function of time, because right now we have, man, my marker does not want to write today. We have r sub t, it's a function of time. We're going to transform it to be a function of theta. And what we're going to find in doing so is that it's going to change the formulation, the mathematical language, such that we can solve this differential equation. But also, when we get a final solution, it's going to make our lives easier in interpreting what the actual orbit is going to look like, because we found with the comet example that it's best to express it as such, okay? So what we want to do is we want to take this differential equation and we want to reshape it. We want to look at it differently. We want to change our mathematical perspective so we can pry our once weighty eyes and give ourselves wings, enhance our analytical ability. That's the premise of this course, right? So how do we actually do that? Well, in order to do it, what we're going to have to do is we're going to have to first transform all the different parameters in here. Now, it's easy to transform this guy, and it's easy to transform that guy because they're just functions of r in and of itself. But what do we do with a second derivative of r? What do we do? What we're going to need to do is we're going to need to transform this over to our new formulation because what we're going to find is that r is now expressed as follows. It's going to be a function of phi, and we know that as time progresses, phi is also going to change. So phi is going to be our time, right? It's going to be a function of time. So this is what our new function is going to look like, and we need our derivative to reflect that, right? Because if this is respect to time, what happens if time changes? Obviously, this guy's going to change, but what happens if phi changes? Time is going to change. That's going to change that, but time can change this guy, which is also going to change that guy, so we have to incorporate that effect into the derivative, okay, which means we have to use the chain rule. Now, in order to transform this, I'm going to do it two ways. First, I'm going to transform the operator, and then I'm going to do it in a more natural way because I found that, some people like to think about it in terms of operators. Some people like to work through right in the immediate step. I'm going to do both just to make sure you guys are on track so you understand what exactly is going on. So the first thing we're going to do is we're going to take a look at this operator ddt. Now, if we put this on r, which is a function of phi, what needs to happen? First, we need to take a derivative in terms of phi because we're saying this is now a function of phi, so it's like r is equal to, that's phi plus phi squared, something like that. Basically, no t's in there. So what happens is it doesn't even make sense to take a derivative with respect to time. So the first thing we need to execute in terms of what we take the derivative in terms of is d theta, okay? Then we know theta is a function of time, so next we need to do the following, right? So when you think about it, it's like canceling these guys out, and that gives us back the original operator. So let's work a bit with this and see what happens. Well, this guy is basically phi dot. So we could take that, throw it out in the front, and carry along this dd theta just to keep ourselves organized. So it comes along for the ride, and we found earlier in this course that this guy, the phi dot, is described in terms of these constant angular momentum L, those constant terms. So what we could do is we can substitute that in. We can say, this guy's going to be constant. It's going to be in terms of this. And we can carry along the d theta for the ride once again. So this is what we end up with for the operator. And I'm actually going to backtrack a bit. What I'm going to say is that we're going to make a new substitution in order to solve this. So what did I say we were doing this? We were doing this to transform it such that we can get rid of this r cubed. What we're going to find is that if we go down this route with just r, it's going to be very hard to solve. So what we're going to be doing is, I'm going to write it here. We're going to substitute, and I'll do this after we transform the ddt, but I'm just making this note just to make this as streamlined as possible. We're going to say, and this is not going to make sense until you actually see it. You're going to see the beauty of it once we work through it. So just keep that in mind. I personally get annoyed when people do this because this is something that was derived just through experimentation. Just try something, see if it works. Try something, see if it works. So you got to trust me here. You got to trust that by working with this, we're going to get to the correct result. We're going to get to something beautiful, and that eventually, you'll see why we're actually doing this. But we're going to substitute, we're going to make the following substitution. We're going to say that U is equal to 1 over R, and we're going to transform this in terms of U, okay? So we're not going to have any R's here, and we're going to want to eliminate this. And what we're going to say is that if this is 1 over R, U squared equals 1 over R squared. So this becomes L U squared over mu d phi. All right? So our operator, d dt, becomes the following, okay? So when we apply that to R, what is going to happen? When we apply to R, dr dt, basically, we just get this guy. And I'm going to work through this a different way now. Instead of, we could throw the R term in there. So it's sort of like this operator is operating on the R, which would make it easy. So, you know, this is very easy right at first. But I'm going to backtrack a bit and work through it manually. So this guy is basically R is a function of phi, and phi is a function of time. And I hope you guys don't hear that car alarm that's going off. Maybe I can edit that out of the video, but we're just going to proceed. We're going to ignore that. We're going to focus on the task at hand. So again, this is phi dot. So that's that guy. And phi dot is as follows. So this is L over mu R squared. And then we have d phi, which becomes dr d phi. Okay, so then the next thing we do is we take this guy. This becomes u squared. And we end up, we see it's basically the same operator applied to R. Now, again, we're making this substitution U equals 1 over R, which I'll explain eventually as to why we're doing that. And we want to actually substitute that in, and we want this to be in terms of U. So this also can be rewritten, R is equal to 1 over U. And that allows us to say that this is equal to L U squared over mu times the derivative with respect to phi of 1 over U. Okay, so very important. This is a little weird. It's going to be a little weird. So what I want to do is I want to write this as u to the negative 1. Okay, so since it has an exponent up here, what we're going to need to do is we're going to need to use the chain rule again, a second time. So think back to, when you're in Calc 101 and you were doing rate of change problems, right? You would basically take the derivative of this and take the derivative of what's inside. Okay, we're going to do the same thing because what is inside can change this. So what we end up with is u to the negative 1. Well, if we take the derivative with respect to phi, basically this becomes basically the negative 1 drops down, and then we subtract 1. So this becomes L u squared over mu times negative u to the negative 2. All right? And then we need to use the chain rule. So then this becomes du d phi, which I believe that's what I did. Yes, it is. Du d phi. All right? So when we try to simplify this guy cancels with that guy, and we find that dr dt is nothing more than negative L over mu times du d phi. All right, so that's what it reduces to. And Next, what we need to do is we need to apply this operator once again. So what I'm going to do is I'm going to erase these guys, and I'm going to write this up just so we have it, on our board space, and we don't forget about it. So dr dt is nothing more than negative L over mu times du d phi. All right, so I'm going to erase these guys, and then I'm going to write that up at the top of the board. And what we're going to do is we're going to proceed with the next portion of what we're doing. So basically trying to find r double dot, because we have r dot. Let's find the next guy. Okay, so r double dot then becomes the following. Well, this is pretty easy. R double dot is nothing more than the derivative of r dot. Well, we have r dot already. And that's, well, bam, that's that guy. So we can say, oh, we know our operator. We know the operator we've been using. We could just basically put this inside and apply our operator to this new guy. So it's a little more complicated, but in essence, it's the same thing we have been doing. So we can get that, and we could apply the operator directly. What I'm going to do, I'm not going to do that. Why? Because that's super easy, right? Super easy. So you could do that. It could be an exercise for you if you like to think in terms of operators. I'm going to do this full force. So we know that this guy, first and foremost, is a function of phi. So this becomes nothing more than d phi of negative L over mu du d phi chain rule times d phi dt. Now, if that sounds weird, if you don't like that, just remember, it's not what is happening, but this is a way to make it make sense in your mind, is you can say, oh, I'm just canceling these guys and still the derivative with respect to time. I'm awesome, right? You can still do that if that makes you feel good about yourself. But what we want to do is we want to say, okay, phi dot is this guy, so we can plug that in. This is basically phi dot. And when we do that, we end up with L over mu, r squared times, we could pull out this constant here, negative L over mu. And then we just apply this derivative to the guy it has to apply to, because again, these are constants. So then we end up with the second derivative of u with respect to phi, and that is equal to negative L squared over mu squared r squared. Now, the reason why I was hesitating was because we could take this r squared and say, I can look at here, r squared is 1 over r squared is u squared. So we can pop that u up there like that. And then we can get our second derivative as follows. All right, so that's what we end up with. And let me check to see if our math is right. Yes, we did it correctly. Good job, guys. So our double dot is going to equal this. And that means we could transform this guy. So our equation of motion then becomes mu times negative L squared u squared over mu squared u double prime sub phi, basically the second derivative, and that is equal to our F term, our force, which we know to be the force of gravity. What happened to that? Yes, that's going to be a positive plus L squared. We're going to take the R cubed. R cubed down there is U cubed. U cubed over mu. Okay. So we get this weird equation, and it's not 100% apparent why we did this or if we made any headway. Well, we made headway in the sense that the R equation we derive at the end of all of this, it's going to be a function of phi, which makes it easier to interpret our result, to determine any kind of shape, and to draw it out. However, what the hell does this mean? This looks harder than the original equation we worked with. So let's work a bit more. I'm going to work backwards, sort of. And what I'm going to do is, first I'm going to say this mu cancels out with that guy. And then I'm going to multiply everything. I'll write it out. Multiply everything by negative mu over L squared U squared. All right. So when we do that, what we end up with is we isolate our U double prime, and that's just going to be equal to negative mu over L squared U squared F minus L squared. No, the L squareds are going to cancel. So that's going to cancel with that. That's going to cancel with that. And we end up with U sub phi. All right. So if we rearrange this a little bit, it's going to be U prime prime sub phi plus U sub theta is equal to negative mu over L squared U squared F. Yes. So this is our new equation of motion. And again, it's not quite clear what in the world we're doing here. But what we're going to find is that this F term, once we put in the force of gravity, which is going to be the negative gradient of the potential energy there, we're going to find that the U squareds are going to cancel out. That's going to give a constant here, and I'll explain this more thoroughly when we do this. And that's going to transform this into an ordinary differential equation, something we can solve very easily, or if you don't know how to solve that, I can explain it to you very easily. So we found by changing our mathematical perspective, the way in which we interpret this R term, this R parameter, it gives us awesome analytical abilities. It allows us to really transform this into something that we have more analytical ability and leverage with, and allows us to streamline this solution. Okay, so we've got this nice equation of motion, an ODE in essence, which I've guaranteed I'll show shortly. What I want to do before proceeding and actually showing that is I want to do a little check to make sure this makes sense with our intuition, to make sure it's converging upon reality. Right? As I've said in my previous courses, my previous videos, so many times before, when you derive an equation, when you derive a result, right? In essence, it's math. It's math that's restricting reality to behave in a certain way. But if you get that mathematical equation or idea or statement and it doesn't converge upon reality, what value does it have? Your mathematical models must agree with what you expect to see because they're describing physical situations. That's what they're intending for. So you want to take simple situations, restricted cases, and make sure it agrees with what you'd expect it to do. So what we're going to do is we're going to take the case in which we have a free particle. Let's assume that we have maybe some satellite that went past Pluto, and it's out in space, and there's no planet, no sun, no star, nothing around that could provide any significant force upon that satellite, that object. In essence, it's going to be a free particle. So what's going to happen is this guy is going to equal 0. The force is going to cancel out. So what you end up with is, if you have a free particle, you end up with a very, very simplified equation of motion. Basically, you end up with u prime prime sub phi plus u sub phi is equal to 0. There's no net force upon it. So if we solve this, what do we expect to find? This should converge upon reality. In reality, we would expect that if it was at rest, it would continue to be at rest. If it was moving, it would continue to move in the same direction with no change to its velocity vector. In essence, there's no acceleration because there's no force. So if it's going like that, it should continue to go like that. Okay, in essence, it should move in a straight line. So our solution here should give us a straight line for r, where we'll have to convert from u back to r. Okay, so before we actually solve this, which is going to be very straightforward, you should probably already know the solution before I actually work to solve this. I want to make note that it should technically really be approximately 0. It's so small that in relation to all these other guys, it's negligible. We're going to take it to be 0, okay? So, solving differential equations. Solving differential equations is an art. In order to solve differential equations, it's sort of weird at first, but what we do is, it's like building a building, erecting a building. We put up a scaffold, a general shape of what it's going to look like, and then we fill in the details of, like constants by making it conform to different laws we have. Basically, we want it to conform to this. We want it to conform to our initial conditions, so on and so forth. So when we solve these differential equations, both this guy and when we're going to solve this, what we're going to do is, it's like we're putting up a building that describes the motion in Kepler's problems, basically planets, comets, any kind of object in space. So the scaffolding we're going to put up is, we're going to put a general shape of how we expect it to behave based upon this guy, and we're going to fill in the missing details. Fill in maybe the walls, maybe the piping, maybe we want a garden outside, maybe we want windows, so on and so forth. So when we solve this guy right here, the scaffolding we're going to put up is what we know to be described by this. So basically this is like u prime prime is equal to negative u. So what that says is that when we take two derivatives of u, we're going to get the same function back, but we're going to have a negative sign. So what does that? What function actually does that? The exponential function, right? So we're going to assume that u sub phi is equal to, we're going to have, some constant that describes it, changes a bit, the details, the features. We're going to have an exponential function, and we're going to have another guy that describes sort of like the velocity, the change, the first derivative in a sense, and then we're going to have our phi term there. That's what we know to be true. That's what we know is the general shape of this guy. Now, let's fill in the details. Let's tackle this guy first, the r term. So how do we do that? We're going to use all the information we have to fill in the details. this is like the blueprint for the motion. Let's use it. Let's use it to build this building up a bit more. So we take this guy, we plug it directly into there, and what do we end up with? Well, if we plug this guy directly into there, the two derivatives, we end up with basically, we take the derivative, the e guy pops out, and we have an a r squared e to the r phi, right? Basically the chain rule, this guy has to pop down. R is a constant, remember, that's a constant, baby. So we get that, plus we just plug it in for that guy, plus ae to the r phi, and then we make it all equal to 0. Okay, so we got these guys, and what we can do is we can cancel that, we can cancel that, and we basically end up with r squared is equal to -1 if we bring that guy over there. So what does that mean? That means that r is equal to positive and negative I, where I is the imaginary number. So if we use Euler's identity, basically e to the I phi, what does that mean? That means we're going to have functions of cosine and sine, right? So what this entails is that u sub theta, our new guy here, this becomes basically u sub phi is going to be equal to cosines and sines. And in this case, we're going to eliminate the sine because we do not want it to blow up, or in essence, we're going to assume we're going to have zero velocity. That helps us crunch out the sine term. I'm going to write it down just because I don't want to confuse you guys. So a cosine phi plus b sine phi. And you probably saw this with the pendulum problem, you know. And what we usually do is we usually end up with the cosine, right? Or it depends upon what you're actually working with. But what happens is if you take the derivative of this, this is sine, this is cosine. And so when initially maybe it's at rest. Initially it's at rest. So when it's at rest, you want it to actually be 0. So what happens is this guy becomes cosine at 0. That becomes 1. So we have u prime is equal to b. So obviously if it's at rest at phi equal to 0, then b must equal to 0. So usually we eliminate that. So we're going to end up with that. So that was like the equation we get when we do, simple pendulum motion, okay? So I'm going to go a bit further, and I'm going to say that, you know what? We're working in polar coordinates, so we're going to have an initial angle. So I'm going to add in a phase angle. I'm going to say that u sub phi is equal to a cosine phi minus delta, okay? That's going to be an initial angle that we're going to use, and in essence, that just really changes this guy out in front. And yeah, it's a nice solution we get. Okay, so this is our general solution. So we went from our scaffolding, maybe we have a building up, it's looking nicer, we're filling in more details, but we still need to fill in some remaining details. We would have to fill in this A term. Yeah, so what is our initial condition? What is our initial condition? And I'm going to pick up my notebook here, so make sure I'm following what I did previously, because I'm doing this off the cuff. What we find is that when we use our initial condition, basically r sub 0 is going to be r naught, right? At phi equals 0. So what does that mean about u? U is 1 over r. So u sub 0 is equal to 1 over r naught, right? Right? Didn't change anything, just used our definition right there. So we can use that to fill in more details for our building, basically our solution. Basically, this is an extra element of our blueprint, the blueprint of the motion of our object. So what we end up doing is we can plug that in. I'm going to plug in that substitution there, so we end up with 1 over r sub phi is equal to 1 over r naught cosine phi minus delta as such. So the last thing left is to actually convert this stuff so we can isolate R. So I could multiply this over there and get these guys all over there. I'm going to just flip everything because I don't want to do that extra step of having to flip this guy afterwards. If you don't know what I'm talking about, just follow along. So if we flip this guy, we end up with R sub phi is equal to, this guy goes up, that guy goes down, R naught over cosine phi minus delta. All right. So for a free particle, this equation is basically telling us how it's going to behave. So you're probably thinking, well, okay, so we started doing this to check the form of our differential equation right there to make sure it's jiving well with our intuition. We expected a free particle to remain moving in the same direction without changing its motion because there are no active forces acting upon it. And it should be a straight line. This does not look like a straight line. You're lying to me, man. What's going on here? So what I'm going to assert is that, yes, indeed, this is the equation for a straight line, but it is in polar coordinates. So let's take a look at what this actually looks like and see what we can figure out about it. So initially, I said that we're going to have an angle of delta, right? So if we have an angle of delta at a length r naught, if we go to our polar coordinates in red, we see we go up an angle delta, we go out r naught, and that's 0.1. I messed up the notation here, so let's fix it. This is not 2. This should be actually 0.1. So we got 0.1, and 0.2 is going to be as follows. 0.2 is going to look just like that. And then what we find is that it's going to move up a angle phi, and then it's going to go out a distance r, right? And it's going to keep changing like that as the angle increases. R is going to change. Okay, so you're probably thinking, that didn't help at all. What the hell is going on here? Well, let's rearrange this equation a bit and see what we can figure out. So we see from this that R cosine phi minus delta equals R naught. So that means that if we had a straight line connecting these points, we're going to assume what we expect. Then this angle between these two lines is phi minus delta. So we got this angle, basically this guy, right there. This is phi minus delta. And if we take the cosine of r, it's going to fall on this guy. Basically, this is going to shorten down to be the base. So what does that mean? That means we have a 90-degree triangle, right? This has to be a 90-degree triangle in order for this to be true. This guy governs, right? So we got this 90-degree triangle in here. I guess I'll circle or go around it. We got that guy in there. And if it's a 90-degree triangle, the line that connects point 1 to point 2 must be perpendicular always to r naught. It must be perpendicular. Otherwise, this is not going to be true. It's the only way it can work, right? We're working with trigonometry here, which dictates that must be a 90-degree angle. Well, guess what? If that's 90 degrees, it means that it is stuck, that this line connecting those 2 points always must be in that direction. In essence, what that means is that this baby right here is an equation of the straight line. So we did some of that work. Very easy, simple analysis, but that was a check to dictate that this equation of motion is giving us the expected results for a free particle. And what that really means is that this is jiving well with our intuition. It's agreeing with what we'd expect. We can proceed with the analysis. We can move on, and we can move on to solving this equation. All right, now that we've run through our check on the free particle scenario, and we verified that the equation of motion here really does describe the situation and the scenarios that we're actually looking at, basically the Kepler problem. We verified this guy. What we're ready to do is to accomplish what we set out to accomplish, and that is solving this equation of motion. So let's proceed in actually solving this for all circumstances that we analyze, not just the free particle circumstance. So how are we going to do that? In order to do that, what we need to do is really put in what this force F should be, because right now it's an unknown. We know it's a function of r and hence a function of u, but in order to actually solve this, we need to get that parameter in there. We need to see what happens, and this is going to illustrate the beauty of why we chose this substitution and how it allows us to streamline this guy and get a solution. Basically makes this an ODE. This is where we figure out why our perspective, our mathematical perspective, how we look at the equation, how we express the mathematical language, pries our once weighty eyes and gives us wings. Okay, so this force, for any central force kind of problem, what we know is that it's an inverse square law. For example, with gravitation, what we found is, from Newton, is that the F, this F guy here, F is going to be equal to negative G m1 m2 over r squared. So it's an inverse square law. In essence, the further away you get, the smaller the force gets, right? That's the behavior and the characteristics of gravity. However, this tends to crop up in other models, other phenomena, other physical situations in which we have this kind of behavior, this kind of situation, and especially with two-body central force problems. The other natural force we tend to see is when we take a look at two charged particles, maybe a proton and a neutron, or a proton and an electron. Sorry guys, I had a brain fart there, in which we have, a positive charged particle, a negative charged particle, and they're attracted to one another. In essence, they have a central force that's acting towards the center between those two particles. So that force, what is that force going to be? That force is going to be K, Q1, Q2 over R squared. Basically, the charges, and this guy, that's the 1 over 4 pi epsilon naught, that kind of guy right there. So this is, in essence, this is Coulomb's force, right? Hopefully you've learned about this guy right here. So this is the same situation that we're analyzing, and we could plug this guy in. Again, it's the inverse square law. The further away they get, the smaller the force gets. It mostly dominates when the particles are very close to each other. So we could plug this guy in there, but we're going to focus on this. I just wanted to throw that in there to let you know that you could use the same model for a different physical phenomena, which is, in my opinion, one of the most beautiful things about physics, because, you can get these models that transcend different phenomena, and it makes you wonder, like, why? Why does this mathematical framework work for so many different physical phenomena? Why? That's a very beautiful idea right there. But coming back to center, coming back to the problem at hand, what we want to do is we want to take this guy and we want to throw it in here, convert it into our problem. So what I'm going to say is that this is going to be represented as, I'm going to let this equal negative gamma u squared, basically 1 over r squared is equal to u squared, where gamma is equal to G M1 M2. Okay, so I'm going to put that up there. Right here, we're going to say gamma is equal to G M1 M2. We got it stored on our board. And now what we want to do is we want to actually throw this in there, okay? So our equation of motion becomes the following. And again, I'm using gamma just because, we could throw in K, Q1, Q2 instead, basically to account for different physical phenomena if we want to use this model, just in case. So this becomes U prime prime phi plus U. I'm liking these curly lines today, phi, and that is equal to, well, let's throw this guy in. So this is going to be negative U over L squared, U squared times gamma, negative gamma, U squared. That's what we got, right, guys? Let's double check. Yes, 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 yes. So look at this. This is the beauty in making this substitution. This is why it works, right? This is why it's so freaking awesome, because you can say, okay, guess what? That U squared there, I'm not worrying about that. Get the hell out of here. So this becomes U prime prime sub phi plus U sub phi, and that is equal to negative mu over L squared. Negative mu, gamma. Negative mu gamma over L squared. And I forgot to cancel these guys. So this becomes a positive. Right like that. And the important thing to note is that this guy is a constant. Constant right there. So we see we have, as predicted, we have that nice ODE that we can solve very easily. Looks very similar to the free particle case we analyzed before. It's going to be a bit more tricky, but we can use the same approach. Basically, we're going to assume a solution, and that assumed solution is like our scaffolding and erecting a building, and then we're going to fill in the details using our blueprints, basically the information we have about the problem and our initial conditions. Okay, so this problem, what we want to do is take advantage of superposition. The physical meaning of what I'm going to do is as follows. On this side, we sort of have like the acceleration of U. And this has to be the force, because if this is like A, we throw in an N there. This is like the sum of the forces, right? On this side, it's a constant. So what we find in a system like this, a Newtonian-based system, is that initially, like if you have a dampened system, a dampened cup and rod system, which is used for a lot of school experiments, if you will. When you first apply a force, let's say you have a constant force, a constant. This force is constant. First, you have a transition phase in which you're counting for the friction, trying to get over that. So it's going from like 0, basically, up to the motion you have for velocity. So initially, it's like, you get, you have that initial period in which you're going from 0 up to motion, up to basically your maximum velocity, and then it's sustained. So what that means is that we have a transient solution and a steady state solution. So our assumed solution is going to be, we're going to assume U sub theta is equal to a steady state solution plus a transient solution. And that's really the physical interpretation of what's going on here. But there is also a mathematical interpretation. So the steady state, basically, here's what's happening. Our steady state solution, let me think about this. The steady state solution is going to be u prime prime sub phi plus u phi is equal to mu gamma over L squared. That's the equation of motion for that. Our transient is basically u prime prime sub phi plus u sub phi equals 0. So you're thinking, oh, what the hell happened there? What? Where's the constant? Well, initially, the system was at rest, and then it goes into motion. So initially, there's no force. So we're trying to transition from this to that guy, right? So technically, we have no force before the force is applied. So if we take this and we say that our solution is like such, and we plug this into here, this is what's going to happen. We're going to see that this works, because when we we plug this in, we have USS plus UT prime prime, two derivatives of that, plus USS plus UT. Again, I'm just throwing it right into here. It has to equal mu gamma over L squared. Well, let's look at this. So if we have USS prime prime plus USS, basically implying that and grouping this, plus UT prime prime plus UT, it better equal this constant. Otherwise, we have violated math, and we are, I don't know what we are, but something is not making sense. So in order for this to be true, guess what? We need these guys to be true, because this is going to be 0. And this says it has to be equal to that. Look at that. Math is nice. We didn't violate anything. It's kosher. It's awesome, man. So we see that we get these double solutions. That's the mathematical interpretation. I explained the physical interpretation. Let's actually put this to use. This is going to be our scaffold, and then we're going to solve everything. So I'm going to put our assumption up here, because we are running out of board space. We're going to assume that U equals USS plus UT. Okay, so what that means is we need to solve this twice. So let's erase this. And you know what? Yeah, we'll erase this also. And we'll erase that guy. So I'm going to write this guy up here. This is going to be our governing baby. U phi is equal to mu gamma over L squared. All right. So let's do the easy case first. Easy case, transient solution, baby. Our transient solution must conform to this equation. This is our blueprint for filling in the details. Guess what? We're lucky. We're lucky. We're lucky, because we already solved this. We solved this previously. So there's a method to my madness. We already know that U sub phi is nothing more than a cosine phi minus our initial angle. Okay, so what I'm going to say, what I'm going to assert is that we are free to exert our initial angle. Okay, so I'm going to say that initially we're going to start at 0. As you could have guessed, that guy was thrown in there to show the straight line. Basically, when we were proving that the free particle is going to move along a straight line. So, let me put in the transient guy. That means our transient solution is A cosine phi. Nice, we didn't have to do anything. Now, let's go to our steady state solution. I'm going to put SS in, okay? So our steady state solution, U prime prime of phi, and I'll put the SS's in this time, must conform to this blueprint. That must be true. In essence, you can think about this like initially we have no force, and then we put the force, we apply it, bam, it's on there permanently. So now we need to solve this. And we're going to take the same approach. We're going to assume a solution. We're going to put up that scaffolding for the final building, the final emotion we're trying to figure out, and then we're going to fill in the details. So this is a steady state solution, and we're applying a force onto this, and we're expecting the motion to conform to that force. Basically, the motion is going to create a maximum velocity, and then it's going to be sustained. It's going to be sustained. So, steady state, what does that make you think of? Steady state, it means nothing is changing. It means we have a constant solution. So, you'd expect that we have a constant, okay? And if that makes you upset, if you haven't taken differential equations before, is something you learn is that if you have this guy on the right, that is a guess for your solution. But just physically, intuitively, it makes sense because when you push something, think about a drag machine. Basically, something that has drag. You push a rod into some kind of system, and it has maybe oil on it, maybe inside of a car, and that oil is resisting it. Basically, initially, transient, you sweep up to the maximum velocity, and then provided that the force does not change, it sustains that velocity. It's constant. This jives well with our intuition, jives well with our physics, our physical idea of the system. So we're going to assume a solution of the form, assume USS is a constant. And we're going to see if it actually solves this guy here. So we're going to assume that we'll call it C1, constant 1. So when we plug the constant in here, the second derivative of a constant is 0. So all we end up with is C1 is equal to mu gamma over L squared. Nice, brah. So that basically says that USS was very easy to find, and that's just mu gamma over L squared. All right. So I'm going to double check that our solution is working here. It is working. So we're getting close to a final solution. Those are our results. This is our scaffold, the general shape of the behavior that we assumed. It worked. It worked for us. Jived well with our math. Jived well with our intuition. We're ready to chug ahead. So U sub phi is USS sub phi plus U transient of phi. And that's nothing more than A cosine phi plus mu gamma over L squared. Now, you're probably thinking, okay, that's cool. That's the orbit of our planets. What does that even mean? What in the world does that even mean? Well, I'm going to non-dimensionalize this. And this is a principle that is used in a lot of physics, a lot in fluid mechanics, and it just helps to personalize a solution or non-personalize a solution in the sense that you can apply it to any situation you encounter because you have fractions, non-dimensional fractions, as opposed to legit lengths. So in fluid mechanics, we have something like Reynolds number. The Reynolds number applies to all situations because it's a fraction, right? It has no dimensions, so it can apply to any situation once you apply the dimensions. So we can have, different behavior, laminar flow, turbulent flow, so on and so forth, and it occurs at different Reynolds numbers. So we're going to do the same thing here. We're going to non-dimensionalize this guy, and I'm going to do that by asserting the following. So I'm going to say that U sub phi, I'm going to pull out this guy, and I'm going to say, well, you know what? This is no more than 1 plus this new parameter, epsilon cosine phi. So, what in the world did I just do? Well, this epsilon, what does that have to be? It must be A over this guy. So, it's A L squared over mu gamma. So why is this a non-dimensional parameter? Well, if we back up to this guy, U is 1 over length, 1 over R. And A has to be 1 over R. It's in front of the cosine. So if A is 1 over R, and this guy is 1 over R, if you take this and put it on the bottom, they cancel each other out. So this is non-dimensional, and it's going to be very important in figuring out what in the world this means. I'm going to spoil it for you. I'm going to call it the eccentricity. And maybe I gave away what the shape is going to look like. We'll go into that in a bit more detail. We need to go over some math before you can understand that. But we get that. And we have to go a bit further. Okay, we're going to have to go a bit further. So I'm going to start going up here. My board is minuscule. And what I'm going to say is that if we take this guy, well, bam, we send it up there. I'm going to say that we're going to have a new length. We're going to have a new length. This is 1 over length. So let's define a new parameter, C. C is going to be L squared over mu gamma. And I hope you guys can see that. So if that's what C is, and we take this and convert it back to R, because that's what we're really interested in. U was used to simplify this nasty differential equation so we could actually solve it. This is what we get. This is what we get. 1 over R sub phi is 1 over C, because we're inverting this, which is equal to that. Yeah. And then we have 1 plus epsilon cosine phi. All right, so if we isolate R by moving it over here, what we find is that R sub phi is no more than C over 1 plus epsilon cosine phi, where epsilon, our eccentricity, our non-dimensional factor, is going to be A L squared over mu gamma. And again, it's sort of like we're just redefining all these constants in here. And C is L squared over gamma mu. I mixed up those guys. That should be mu gamma. So that is our final equation for the orbit of planets. Okay, so what did we accomplish here? We accomplished a lot. By changing our mathematical perspectives, the way in which we interpret our equation of motion and our mathematical language, we were able to drastically enhance our analytical abilities. It allowed us to take this nasty ODE and convert it into an ODE, an ordinary differential equation that we can solve. That's awesome. But you're probably thinking, we got this guy. I don't know what it means. What do we figure out? What are the orbits going to look like? Well, what we're going to do next is we're going to take a look at different geometries and how they're defined mathematically. And we're going to compare it to this and see if this looks like any of those mathematical interpretations of geometry. That's going to help us discover how the motion looks, help us discover Kepler's laws, and really finalize this discussion. It's also going to help you understand why I use these parameters, these guys here, and why I'm using this eccentricity. Okay? So I hope you enjoyed the discussion. I hope it was fun. Stay tuned for a final interpretation.